and first introduce what a node and an edge is. So think about a node as points on a graph, like a 2D graph. So if you have a bunch of points and you want to connect these points with lines, then imagine the lines are called edges. So that's kind of the abstract visualization of what a graph is. And wait, Anna, where's the, we have chalk. So then, as you can see in the picture, we have 6 nodes. So nodes are denoted usually by circles. So we can say like 1. So that's a node. And then if you want to connect nodes with a line, and then this line is called an edge. So hopefully it's pretty straightforward. And a graph can be used to represent many different types of situations. So for example, you can imagine these as, let's say, houses. And then each edge between a house denotes the path between each house. And I think it's good to mention here that each edge can also have a weight. So there's either unweighted edges and weighted edges. So what a weighted edge simply means is that each edge has a number associated with it. So here we can put the number 5, and that just means, okay, if we want to go through this edge, we'll have some sort of number, in this case 5, that corresponds to whatever problem you're trying to describe. Okay, so maybe that might be a little confusing right now, but going back to the house example, let's say you have house 1 and 2, and then the edge connecting to them is 5. So you could just say, you can visit house 1 from house 2 with a walk, like a 5-minute walk in between, for example. So it's pretty abstract, but that's what a graph is. Okay, so any questions so far on what a graph is? Okay, cool. Okay, so then for slide 6, you can see I defined 2 different types of graphs. So there are directed graphs and then undirected graphs. And a directed graph, you can also call a digraph. And what this means is that each edge has a direction to it. So if we add an arrow to an edge, it becomes a directed graph. And then undirected simply means that it can go in both directions, like that. But since drawing 2 arrows, that's more annoying, you can just not draw an arrow, and that just implies that it's undirected, which means you can go either way in the graph, on the edge, sorry. And then you can take a look at the pictures that should help with your understanding of what a directed graph and an undirected graph is. And then a special type of directed graph is also known as a directed acyclic graph, also known as a DAG. So this is a very important type of graph that pops up a lot. And what this means is that it's a directed graph where there are no cycles. So for example, if we drew another graph like this, you can see that if you start from any node, you can't follow some edges and go back to the node you started with. But if we drew another edge like that, then you can see that there's a cycle. So that's not a DAG, because it is directed, but it has a cycle. Okay, so are we clear on that? Okay. Oh, question?
So in the directed graph, are all the edges like have a direction, or in some edges the both are have like both I guess both directions.
Yeah, that's a good question. So in a directed graph, every edge will have a direction, but if you wanted an edge that you can go both directions, what you would do is just add another edge like that. So that's how you represent going both ways. Yeah. But then you can see that this also is not a DAG. because this is a cycle. Okay, so if we're clear on graphs, we can move on to the definition of a tree and then some of their properties. So a tree is an undirected graph where there are no cycles in this graph. And this is a little different from a DAG because in an undirected graph, you can go both directions. So that means as long as there is a component like this, where it's all connected, that's a cycle. And we don't want that. So you'll notice that a tree will end up looking something like this. And there's no cycles. Okay, so that's a tree. And then a binary tree, they're going based off of its name, binary. That means that each node has at most two, in this case, we say two children, but I'll go over in a sec what a children is. So this is a binary tree. And what a child is we have a bunch of nodes, and a child is simply a node that is connected. Just think about it under your current node. So if we're at node 2, can someone tell me what the children of 2 would be? 4 and 5. Okay, yeah, that's correct. Okay. And then I'll first skip the binary search tree because I want to go to slide 9 just to talk about the terminology before going back to explaining what that is, a binary search tree. So first, I've gone over what a node is. That's just the, think about them as points or circles, and then nodes are connected by edges. And so we get to what a root is, and the root is simply the top of the tree. So if we have a tree, you can root it, so quote unquote root the tree at any node. And what that does is you put the node on top and then you draw everything under it. So in this case, this would be the root. So this is the root. And then if we were to root the tree at 2, it would look a little different. Let's see. So it will look like that. Okay, so does that make sense? And notice that since 2 has 3 children now, it's no longer a binary tree. Okay, and then next we have children. I think we're all clear on what exactly a child is. So the children of 2 would be 1, 4, and 5. And then the children of 1 would be 3. So you can think about it as like a family tree. So we have parents and then the children underneath. And then that brings us to the 5th point, what a parent is. So the parent of a node is simply the node on top of it. Okay, and then siblings are just all the nodes with the same parent. And then, so the depth of a tree, the depth of a node is the distance or the number of edges from itself to the root. Okay, so what is the depth of node 3 in this case? 2, yeah, so the depth equals 2. And this is because there's 1 edge and then 2 edges. Okay, and then next up we have the height of the tree, and the height of the tree is fairly straightforward. It's just the maximum depth of any node. So in this case, it could just be, think about it like this. So that's the height. Okay, and then the leaf of a node of a tree is all the nodes with no children. So notice that they're all the leaves are on the bottom, so the very bottom level. So these are leaves. And then a subtree. So the definition of a subtree is assume we root the tree at some arbitrary node. So let's use node 2 here as an example, but then you forget about everything not under the node. So just think about it like this section, and that is a subtree at node 2. So the subtree of 2. So it's just some section of the tree. And so the subtree of a single node would also include itself. So subtree of 5 is just 5, subtree of 4 is 4, and then the subtree of 2, well, 2 is the root in this case, so subtree is just the whole thing. Okay. Any questions? Okay. So then we can go back to slide 8 just to talk about a binary search tree, because this concept is very important. Pops up on interviews a lot. So a binary search tree is a binary tree, except every single node also has a separate value associated with it. So let me just erase this word. Okay, so let's assume that we have a binary tree like this, and all the node numbers, those are just for convenience, so you can reference the node, and we know which node you're talking about. But then now each node also has a value with it. So let me write some arbitrary values like, okay, actually, yeah. Okay, so here we have a value of 2 associated with node 1, a value of 10 associated with 2, and then 5 with node 3. And the property of a binary search tree is that the number of the left child of a node is always smaller than the value of the node itself. And then the value on the right side, so the right child is always bigger. So in this case, this is not valid because as you can see, 10 is greater than 2, so it doesn't satisfy the binary search tree property. So if we were to make this a valid binary search tree, we can have 4. Okay, so we can have something like that. Actually, you can just put, say, 41. Okay, and you might think, why is this important? So if I were to ask you, find a number in this tree, how would this possibly help? Yeah.
Wait, oh, no, I don't know.
Yeah.
Oh, it is always-
Or I don't know if that's the right word, but it's faster because like you can just figure out whether you have to go left or right instead of traversing through all of the nodes.
Yeah, exactly. So that's why it's called a binary search tree, because
It's better than search, right? Okay.
yeah, so it helps you with searching, and it's a lot faster than just going through the whole tree. Okay, and then on the very bottom of the slide, you can see that there's a small table. A question?
I have a question, but
Yeah.
how would you be able to use like binary search of this tree? Because if you like go to the right and then go to the left, the like lower left node could be smaller than the root. So it kind of defeats the purpose.
Right,
Does
right.
what I'm saying make sense?
Yeah.
So how does it help you do binary search if that's the case?
Did I draw this wrong?
When you would insert something like 41, I don't think it should go down the left. Same thing with like the 3. So like, if you think about how those elements would be inserted in a binary search tree, the 41 should probably go down the right of the root.
Yeah, right. Okay, yeah, so I think I drew it in valid tree. Yeah, let me fix this real quick. Yeah, so the reason why the previous tree I drew was not valid is because when you're inserting numbers in this tree, let's say we have this configuration right now, but these two don't have numbers, and you want to insert, let's say a 3, right? Then you would check the root and you say, okay, 3 is smaller than 4, so you go down the left side. Okay, and then you compare it with 2, but it's greater than 2, so you would go this way. So I had a 41 here, but you see that that's impossible.
Yeah.
Okay, so if we had 41, we would check with 4, it's greater, so you go on the right side, and then 5, it's greater, so you would write it here.
Okay.
Okay,
That makes sense.
and then you can put something like, well, I guess that would work because that's 4, but
Just put like a decimal number.
okay. So we can put, yeah, let's just put 6 and 5. Okay, so hopefully that makes more sense.
Mhm.
So you can now quickly search for a number just by following left to right. Okay. And so using the table on the bottom, accessing, you would just go through and binary search. So use the properties of the binary search tree to access a node. And then searching, it's the same thing. You just go left or right, depending on if it's greater or equal than your target number. Insertion, you would just kind of similar to what I explained before, just check starting from the root if it's greater or equal, and then either go left or right and then add the node at the end. So if I were to add another node called 42, then you would compare with 4, 6, and 41. And then you find that it's greater than 41, so you just create a node here like that with a value of 42. Okay, so are we clear on that? Okay. And then deletion is the same thing. You just go through, find the node you want to delete, and then remove it. But notice that here it's these slides has SBBST, and that stands for self-balancing binary tree, which we won't be talking about today. But just think about it as a binary tree that rearranges itself and also rearranges the nodes such that the height of the tree is always log n. So height, this is always log n for a self-balancing binary tree. So always just balances itself such that the height is log n. And this way, because the height is always log n, you would go through at most log n nodes per search. And thus the time complexity is log n in this case. Yeah, the important part is it's only true for this. Otherwise, you can just keep adding in a long chain. So searching would just be worst case going through everything, which is not too good. But that's how ordered sets and maps are implemented using that. That's just a insight into how exactly the libraries in C++ work. Okay, so any questions on this before we move on? Okay, I think we're good. In that case, we can move on to slide 10. So slide 10, we have 3 pictures. And could someone tell me which of these pictures are a tree and which isn't?
Very sorry.
Slide 10, you're asking for what?
Which is a tree and which is not a tree? Yeah.
The top 2 be trees and then the bottom one's not a tree.
Yeah, that is correct. And why is the bottom one not a tree?
Because it has a cycle.
Okay. Yeah, so that's correct. So that was just some practice on identifying a tree. Okay, so then for slide 11, I'll go over what, well, I went over what a subtree is, but I'll go over why subtrees are so useful. So in this case, let's say we had a problem that involves, let's say a binary search tree. So we can just take this example and we want to output the sum of all numbers in this tree. So we would want to add 1, 2, 4, 3, 5, and so on, and output that sum. So what you can do is break down this tree into subtrees. And then using recursion, you start from the root, break it into 2 subtrees. So the subtree of 2 and 3, and then break those down into subtrees of 4, 5, 6, 7, and 8. So you keep going down from the leaves and then you combine them to find the final answer. So as a visual to illustrate that, we can imagine that we start from, or we break down the problem down to the subtrees of 4 and 5. So this would return 1 and this would return 3, right? Okay, and then we return back to the subtree of 2. And we get 1 and 3 from its recursive calls. So then we add them together, we get 4. And then you add 4 to 2 because that's the value of node 2. So you return 6 in this case. So return 6. So return 6. And then the same goes for this way. We break down the subtree down to 8. So it returns 42. And then here, this one returns 83. Okay. And then you keep combining them. So this one returns 88. And then you add 6 because that is the value of 3. So this returns 94. So in the end, you add 6, 94, and 4. So you return 104. And that's the sum of the whole tree, which is what we want. Okay. So for the sum. And that's just an example of breaking the tree into subtrees and then combining the answers. But some problems involve a little more than just adding 2 numbers. So for example, let's see. Like some problems, you might have some return value for the left subtree and right subtree, and you want to compare them and see how many numbers add up to 5, for example, and then you would continue and do that. So it's not always as simple as just adding 2 numbers. That's the point I want to make. Okay. Wait, Anna, how do I log in again?
To have my fingerprint.
Oh, okay. So let me see. Okay, so if everyone's clear about how we use subtrees, then we can move on to slide 12. And slide 12 is just a fun definition about what a forest graph is. This usually doesn't pop up, but I think it's nice to know what a forest is. And a forest is exactly what a real forest is. It's just a group of trees. So if you have this tree and then you put another tree next to it, then that's a forest. Okay, so I think that's clear. And the one thing to notice about a forest is that it's actually a single graph and it has multiple nodes because each tree has its own node. Root, sorry. Yeah, root. I meant root. Okay. So any questions before I move on to graph traversals? Okay, I think we're good. So let's move on to slide 14. And here I'll talk about two different types of graph traversals. Can I erase this board? I just erase this.
Did you just pull this button and his Z went down?
That's true. Okay. So we have two different types of traversals, BFS and BFS. So BFS stands for breadth first search, and that just means that we're traversing through a tree by level. So if we have an arbitrary tree like this, then we would first check this node, then these nodes, and these nodes. So that's what BFS is doing. And then as for DFS, so this is DFS. And then for DFS, we travel by going from the root all the way down to a leaf, and then backtracking. So we would go something like this, and then we would backtrack to here, and then go down to these children, backtrack, and then so on. So this is BFS. So just to be clear, BFS goes level by level. So essentially depth 1, depth 2, depth 3. And the DFS goes all the way down one path and then tries all the other paths by going back from each node. And then if you want, or if you're still a little confused, you can check out slides 16 and 17. 16 is pseudocode for BFS, and then 17 is pseudocode for DFS. So just to briefly explain both of them, the pseudocode for BFS, we implement that with a queue. And first we push in the starting state. So a state in this case is just a node. So we push in the root, and then in every iteration, while the queue is not empty, we take the front of the queue, so that's the top of the queue, and then we push in all the neighboring states that we haven't pushed already. So in this case, we push in the top one, so we push in this node, and then neighboring nodes, I think I forgot to define that, but it's just any node connected by one edge to our current node. So the neighbors of this node would be these two. So we would push them in because we haven't pushed them in the queue. And then we would check this node, push in all of these, and then we check this node and push in this one.
Great.
Yes.
Okay, never mind. Yeah.
When you said, when we're checking, do we checking if it's not empty? Is that what we mean by not, we're checking?
Well, so we have a loop. So while the queue. So queue is if I check, you mean this one or checking when you push in new nodes?
Yeah, when you're pushing in new nodes.
Oh, okay. So for that case, you just check whether or not you've pushed it already.
Oh,
And you can do that multiple ways. So if we're to assign numbers, so these are a bit small, but let's just say 4, 5, 6, and 7. Then we would first push in 1. So Q, we take 1, cross it off, and then we check its neighbors. And in this case, it's 2 and 3. So you add 2 and 3. And then you check the front of the queue, which is now 2. So we mark that as processed, or something like that. And then you check the neighbors of 2. So it's 4, 5, and 6. And then we get to 3. We do the same thing. So we have 7. So do you see that because we have a queue, this is one depth, this is one depth, this is one depth.
okay, that makes sense.
Yeah. So that's BFS. And then BFS is a little similar, as you can see from the pseudocode. We're also checking each neighbor and then going to it if it's not visited yet. But the only difference is we're using recursion. So we're recursing from here, 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 and then if we have no more neighbors to go to, then we just backtrack in our recursion and then proceed from there. So any questions about BFS or DFS, or maybe about the implementation?
Why do you do BFS or DFS?
Oh.
Why choose one over the other?
Okay, so there's some problems are better to use DFS, and then some are better with BFS. But I'd say usually BFS is better if you don't know where your answer is. So let's say your answer is on level 4, then you know that BFS will run all the way to level 4 and it doesn't care about anything under it. But DFS might be bad because let's say we have a node 8 here. But BFS possibly, if you mess up, it's going to go down this path. And let's say there's infinity nodes down this path. Then that would be very bad, right? Because it would keep going down this path. It's like a huge number, and then it would backtrack all the way up, go down this path again, backtrack all the way up until we find node 8. So that is a lot worse than just going through 4 levels. Does that make sense? Okay. iPad locked again.
Oh my God.
I think it's close, yes. Yeah, so this explanation was what slide 15 was trying to represent. And then one more thing before we have our break is different types of DFS. And we have 3 different types of DFS. And the only difference between them is just the order in which you process the nodes. So first we have pre-order, and pre-order, as you can see from the slides, we have current, left, and right. So what this means is that if we're at some node, using this example, let's say we're at node 2, we would first process 2, then process 4, and then process 5. And then going off of the other traversals, we have in order traversal, which means we first process 4, 2, and then 5. And then for post order, it's just slightly more different. You process 4, 5, and then 2. So usually it doesn't matter which order you use. Some problems might ask you to just print out the pre-order traversal order, for example, and that is just running a BFS and just printing out the nodes in the order that you encounter them. So I just want to make that clear. There are 3 different traversals, so traversal orders for DFS, but usually it doesn't matter too much which one you use. Okay, any questions? Okay, so in that case, we finished talking about graphs, trees, and their properties, and then some of the graph traversals. So we can take a short break right now, and then after the breaks, we have some practice problems about how to use BFS and DFS. Okay. So why don't we take a short break and then we can come back.
Stop recording.
Did it stop? Pause recording? Yeah. Did you pause? Oh, I didn't yet. I think we need to give back the charger.
Okay, so given a graph, check if it's a tree. It's a very short problem. But yeah, how would you approach this problem?
Check for a cycle. Multiple like starting like nodes. Like,
No, so let's just assume it's a tree with one root.
uh,
And if you notice, the property of a tree is that, let's say you have 2 nodes, then there's always one path and exactly one path between them. And that makes sense, right? Because there's no cycles. Okay. Did you have your hand raised?
I was just gonna say use like 2 pointers to like make sure there's no cycle, but then never mind, that doesn't work.
Yeah, that doesn't work because there's no cycles.
But we're trying to check if there's like.
Yeah, but how would you use 2 pointers? Because it's not just one chain. A tree can have multiple chains.
Yeah.
Or could you try using breadth-first search and see if it's new pops back up?
Ooh, yes, yeah, that's good. That's good. So the idea was to use breadth for search, so BFS, and then we start by pushing the root, and then we perform our search, right? But a cycle only exists if we pushed in a node that's already visited. Right, does that make sense? Because let's say we have this tree. And then we have this edge. So that's a cycle, right? But then once we get to node 2, we're going to push 8 in our queue. So let's just insert 8 here because it should be. So we visit 8, And then next we visit 4, and then we visit all the neighbors of 4. But guess what? 8 is a neighbor of 4. And 8 has already been visited. So you know that this is a cycle. But then there's also something to pay attention to. And that's when you store this graph, usually what we do is an adjacency list. So if you're not familiar with adjacency lists, can you raise your hand? Okay, so an adjacency list is just, imagine we have an array and so on. So these are the node numbers. And for each one of these positions, we have a list of other numbers. And this list corresponds to the nodes that connect to each one of these nodes. So for 1, we would have 2 and 3. For 2, we would have 1, 4, 5, 6. Okay, and then what would 3 have? 7. And 1, yeah. Okay, and then we fill out the rest the same way. So this is known as a adjacency list because it stores the adjacent nodes and it's a list. So that's where the name comes from. Okay, so then there's one problem if we do BFS here using the solution with BFS. And let's assume at every single step we check this list. So we check through this list and then push all of them in our queue because they're the neighbors, right? But can someone tell me what the problem would be here? If our solution was to go through for every node, push in all the neighbors, and then check if that neighbor is visited. So as a hint, let's say we're at node 1. Okay, and then we push in 2 and 3. And now we're processing node 2. So we go through 2. So what's the first number we push in? That's 1, right? Okay. But what node have we visited already? 1, okay. And that's bad, right? Because this is technically not a cycle, 1 and 2. So do you see that that's a problem? So what we can do here in this case is, well, there's many different solutions to this, but one of them would be storing, instead of single numbers, we can store pairs. So, and what the second number here represents is the parent of our current node. So we would store 2, 1 because 1 is the parent of 2. And the only difference here is that while we're going through this list, we just ignore the parent. Because we know that we always visit the parent before the child. So if we ignore that, then we can just use the solution and it works. Okay. And do you think that the solution also works with BFS?
Oh, I don't know.
Yes. Okay. And why do you think that?
Is DFS like also spans the whole tree? Just in a different order, but I don't think the order for that.
Okay, yeah, so that's correct. DFS also works. And if you look at slide 21, that's just a short C++ code using DFS that checks or returns true if it is a tree, if the graph is a tree. So notice that the first line of the code is just denoting the maximum number of nodes. And then the second line is our adjacency list. So we declare an array of vectors. So the first dimension, this is the array, and then for every single position, we have a vector. So that's the adjacency list. And then here we have another Boolean array called vis, and that's just checking whether or not we visited this node already. And then if you can look at the function parameters, you can notice that we have a node in parent, which is similar to the pair in the queue. Okay, so any questions about the warm-up problem or the code?
Wait, would this work if two of the nodes have the same value?
Well, so when you label these nodes, you never want two of the nodes to have the same value
Oh, okay.
because remember, these are just indices. So if you have two of the nodes of the same value, just rename one of them because they should be unique. If this one was 2, for example, and I say, oh, we're at node 2, which one are we at?
Yeah.
We don't know, right?
Okay, got it.
Okay. So if everyone's clear with the code, we can move on to the first problem, practice problem. So this one's called symmetric tree. And in this problem, we're given a tree, a binary tree. So remember, each node has at most 2 children. And we want to output true if it's symmetric and false if it's not. So if you look at the input on the left side, that's an example of a symmetric tree. And then the one on the right is not symmetric. Because if it was symmetric, we would have the 3 on the right side as the right child. Okay. So why don't we spend maybe 1 to 2 minutes thinking about this problem, and then we can come back to see if anyone has any idea.
So in this case, we preferably would not use Bfs. I guess you could, but I would use recursion.
Yeah.
I don't
They just.
Right, so right, so if you do low button.
Yeah, that's why I'm not active.
In this case, like if I had to, I would check that. Then what I do.
Yeah.
So I would have the little case, and then I say that, okay, well, is this guy equal to the
What's the next?
Yeah.
Every time I check what's the next one, it's like a file.
and after I get all these, but then now it's just tricky because you're comparing
Yeah.
this one, now that he's really two nodes of trees, you want to split, you want to see 3, but you want it on the outer. Yeah, this is.
Oh, yeah, I did some. By the way, A with a bad yeah, but only because you couldn't force it because in the past cases like max. They were like more in it was you could have CVs.
So, it also makes
Yeah, I mean, I had a patient. So it's just things like that. But test kit is
So, in this case, we're multiple workers.
because I looked after like test kits is like 28,000.
Column left hand, right? So, we want to switch your train. Like,
Also, I realized like
current child,
my
like,
own
my
computer
current
Python is so
child,
slow.
my left child is going to.
It's like if you're doing diagrams in Python, it might actually be better. Like use the set priority for like. Yeah.
But it's not just equal because we actually want it to be first. Right.
Yeah.
Well, I
Okay,
guess
so
that's-
does anyone have
it was actually just here.
any ideas on how we can approach this problem? We talked about the problem?
Me,
I guess we could do it like recursively.
Uh-huh.
And like have like a left and a right node, and then if you recursively call a function, but the left one, when you move left on the left one, you return like right on the right one, and vice versa. So if you go right on the left one, you go left on the right one. You just check if they're equal every recursive call.
Okay, yeah, so that's correct. So what he's saying is that we have a function, imagine the Bfs function. You can also refer to the pseudocode, but we have Bfs, and then we have, let's say node 1, and node 2. And then at every single step, what these two are representing is node 1 represents the node on the left side, and then node 2 represents the one on the right side. So if we go from node 1 to the left child, so just imagine like that, we instead update node 2 to its right child. And if one of them doesn't exist, actually, so if the left one doesn't exist, check the right side. If it exists, then you have a problem. If both of them don't exist, then we're good. Otherwise, you just repeat, recursively call this and then check the values at each node. Okay, so does that make sense to everyone?
Check the values.
Yeah, because each node has a value in this case. So in the problem, the numbers aren't actually the node indexes. They're just values, yeah. Okay, so everyone clear on this problem? Okay, so in that case, we can go on to slightly harder problems. Okay, so the second one is we're given a binary search tree. So as a recap, remember the properties of a binary search tree. The numbers in the left side, so the left child, are always smaller. The numbers in the right side are always bigger than the current node's value. And then, so we're given a BST and you want to output the sorted list of these numbers. So I guess we can just try and think about this together. So first, would you say, would we use DFS or BFS for this problem? DFS? Okay, and why is that?
If I just think of like the first traversal DFS, we can have it go all the way down the left side, the leftmost. And in a binary search tree, that should be the smallest term in the list.
Okay, and then?
And so the order of the traversal would have to be specific, but by going down the most extreme like path, we should be able to like hit extreme values properly in the proper order.
Yeah, okay, so that's one way to think about it. The other way to think about it is we know that BFS travels in levels at a time, right? So if we just visit the first node, we actually don't know where exactly it is in our list. So what we want to do is go all the way down the left and then backtrack from there, because we know that the node all the way to the left is the smallest one. So that implies DFS. Okay, so if we know it's DFS, my bad. You want to do it?
Sure. Or we can ask the audience,
Hint.
yeah, hint, which one of the three would you use for this? Given a binary search tree. So maybe it would be helpful to draw like a BST on the board so we can.
Oh,
see
it's
what-
on the slides too.
Oh, it's on the slides, okay.
Yeah, so let's just say the binary search tree in the example. So input.
Yes, which one of pre-order, in order, or post-order would you use?
Probably,
Pre-order.
probably in order.
Is that, you agree? Is
Oh,
that a
I'm sorry.
hand? Is that a cup? Hand, both hands?
It's just the one, whichever one calls the recursive function first.
Recursive function first.
Oh,
Okay, so let's do it with pre-order first.
Pre-order, well, okay, so let's just
Just draw it,
imagine.
Justin.
Okay, let's just imagine you have a very small BST.
Okay.
Start on a very small.
Okay, so pre-order, you can see on top, current left and right. So if you're at 2, the current is 2, right? Current, left, right. So does that look sorted?
Not really, actually.
Yeah, so that's not sorted, right? So the properties of a BST left is always smaller than this, which is always smaller than that. So does that tell you anything?
It should be in order.
In order is left, current, right. So yeah. So we want to do, this one first, and then this one, and then this one. And that gives us 1, 2, 3. Okay. So that in our implementation, we can still implement DFS the same way. Except the only difference is the where you put your print function or whatever you're trying to store. So if you had right here, DFS node. Okay, and then we have all the neighbors. That is a parent. Actually, no, I did not do. So then visit left child and then visit right child. Okay, so that's the framework of the DFS. So if we want in order, where do you think we should print out node? Yeah.
Right after visiting the left child.
Right after visiting, okay. So we print out node. Okay. And the reason we want to do this is because we want to visit the left child first, process all of them, then print out our current node, then visit all the right ones. Okay, so does that make sense? So first we establish the order in which we want to print this, this BST such that it's sorted, and then we can just code up the DFS. Yeah.
But for the example in the middle of but it doesn't kind of order.
You mean the one on,
Like the
does
top.
it convert?
Yeah, like the one top.
Oh, that one is not a BST.
Oh, wait.
So like a BST on the left.
Yeah. Okay.
Okay, so everyone clear about this problem? Right, so it's just in order, and then since we do left current and left current, right? Okay. Okay, so in that case, we can move on to territories then. That's the third problem. Yeah, this one's slightly different than the last two problems because we have a grid of numbers now. But think about a grid as a graph. So every spot in the grid is a node, and then it's just connected by an edge to every adjacent position in the grid. So not a tree, but still a graph. And in this problem, we want to find the number of regions or territories in this case. And a territory is just a block of numbers that are the same. So if you look at the input, you can just outline the shapes of all the ones and the threes and then count how many of these shapes there are. So that's what the problem is asking for. Okay, so why don't we spend 2 minutes trying to think about the problem?
I don't know. Probably, I think. Actually, I don't know. This was just 2 days. I mean, did we just get it? I thought it was like 100. Oh, okay.
Do you have one question?
I lost it. I don't know what DFS means.
Oh, core.
Well, I think
No.
this is more.
Yeah,
so it's
Go
going to go
like that.
It's like this one, like you go here, right, and the left comes down here, and then right in there, you go from there.
How do you say goodbye?
Wait, this is like what?
This is not one.
Wait, I'm.
I do it. Speak it.
What
No,
DFS.
Speak it. I mean, it's supposed to. I'm just not that good.
I don't know if I feel like DFS.
No, I can't.
I think you start with this first one here. And then
Like, I
you
can
go-
understand
you
it,
go-
but.
You go this direction and you go down, and you go horizontally vertically, and you try to do the same. As the sky.
Yeah, this
And
one's
you
big,
do the
but-
same thing for each other.
Yeah.
Some people
love
love
to
to,
do
you
goodbye
can't
because they never leave.
go to other ones, or actually,
You say
maybe you
goodbye
know,
and they
I
come
want
back.
to. Yeah, never mind.
I like that.
You're not the only idiot.
Oh, yeah. That's it. That's it. But like, no one actually like.
Maybe it's like 2D ground, like, this is like-
Maybe just like the line. Cause like, it feels really English. People say bye.
Well, how many do you 10 notes? I can
Barely.
barely do 10.
This is English, but I don't know.
Really?
I mean, that's only like I can't do it. I mean, like,
Shut up. My pinky is pretty.
I know.
Stretch.
No, I think it's good right now, because every time you visit one of the kids, it's like their last one.
I don't know how to do it. Wait, I always use these too. Yeah, I'm serious.
Really?
Yeah. Alright, let me just look it up. Maybe I do know.
What's the?
I don't know the name.
Why do you use?
Wait, I don't, just what they use, like, yeah, that's basically.
Yeah, Bloodfill is DFS.
What the heck is what?
You flood stuff. It's like back then in.
Water,
Okay. I mean, I'm not in the best of like patronizing explanation. Are we just talking about like a program or just?
Floodfill is an algorithm.
Okay. Okay. So did they say DFS or DFS? Also added.
I think it's DFS, because, okay, I'm not looking, let me try to explain it, I'm pretty sure you start with the first one, and then you check the horizontal and the vertical, basically, this way up, down, like all the way, unless it's like hitting outside boundaries or it's going down. Then you go to the next one and do the same thing, and you keep doing that, and at the same time, you also mark the visitor graph. And then you continue to do that until you reach like the twos, I guess, and that counts as one, right? And then after that, you go to the next one, I believe.
Oh, we just wanted to like, no,
Yeah, so we started here, right? And we marked that as visited, we also marked this as visited, right? But we still go here, we check that
I
as
mean,
visited. When you
oh,
go to this, when you go to the next one. I don't know. This is-
Sorry?
I think it's-
Oh, no, I could get more.
I believe so. I might be wrong, I feel like I got that right.
So just assume up to n squared numbers.
I don't know.
I was like, what?
Okay.
Yeah,
Wait,
I was thinking of.
I said.
That's pretty obvious.
Oh,
So maybe I should have gone, like,
Yeah, I think that's probably.
Whatever you see.
But then as for traversal, that idea.
Oh, yeah, okay.
okay, let's go, are you now, you're trying.
I was thinking about. Oh, am I asking questions?
We kind of did.
So we have 20 minutes to go over this whole problem.
Yeah.
Yeah, that's just more. Because
Idea.
we abstract each.
Allah.
It's fine, yeah.
Hey, Allah.
Can you find?
No, we're not getting.
Yeah.
Just write pseudocode.
I'll go over the solution for this. Does anyone have like ideas of how you might do this? We all read the problem, right? Yeah. Yeah, go ahead, go for it.
We have to have a separate like 2D or for the visible, right? Or-
Yeah, that's fine.
And then we basically, we go through each point and then at each point we check all 4 directions and then we traverse. Exactly.
Yeah, sure. But what do you do when you traverse?
Like if it matches the same number, then we go to, we change the, we make the current one the next one. That's the same, and then we check all 4 directions and then we keep doing that till we hit a different number or we're out of bounds.
I think that worked. Wait, Justin, did you hear that?
No.
I don't know if it makes sense though.
She's saying that you traverse it and then you check your visited. Wait, so your visited is a Boolean or an integer, right?
Well, we do a Boolean too, right, basically.
Oh,
And every
okay.
time you visit a spot, you just mark it true, and then you go to the next spot, and if it's visited already, you can just skip it. and keep
Yeah. Oh, yeah. I think this is basically the solution. Yeah.
Yeah.
Yeah. So you basically.
Bfs, right, at every spot that you can.
Yeah.
Good job.
Okay, yeah. So I'll just try to code this up. Should I do this on the whiteboard? It doesn't matter.
Pseudocode is fine.
Pseudocode is fine.
Yeah.
I should have told him that earlier.
Yeah.
I did.
You could just only do what?
Write pseudocode.
Yeah, sure. I'll go quick then.
Because the next 2 problems are pretty good.
Okay.
Oh, also, isn't this n squared then?
Yeah, but the input is already n squared or nm. So no, any solution is going to take nm time.
I see.
We go through all of this.
Yeah. Just like read the input would take nm time,
I see.
and that's like the best we can
So
do.
that's like allowed, right?
Yeah, definitely
Oh,
allowed.
yeah.
Some questions will just have like an n squared answer, like only an n squared answer.
Okay.
That's okay.
Sure.
I mean, this is basically pseudocode for like the main function. It's still like it's something to do with DFS function, but this is basically how it would work. Where what you do is you first initialize a scene or like a visited. We call this visited scene. Doesn't really matter, but you initialize that boolean, and what you do is you start at the count of 0, and then you loop through your graph or the territories. And so if you already seen it, you continue, which means that some other DFS from a node has already seen it. So that means you know there's a path from something, some previous node to that node that you're looking at. So you continue. Otherwise, you know, you haven't seen this node, which means you also haven't seen this component yet. So we add one. Also, I should like update this. We add one to the count, and we also make sure our DFS, what it's going to do, it's going to take the graph, it's going to take the node, and just visit all the nodes that are connected to it and update our scene. Update our scene function. I mean, sorry, our scene array, right? So because that way, I mean, we know what's connected to the node that we're looking at. I'll need to do the DFS, do I?
No.
No.
But I guess you have to specify you're passing it like by reference.
Oh yeah. So like the functions, the signature of like a DFS would just be like it's getting long. Yeah, so this is like the function signature for the DFS. We have to make sure we pass by reference. That way, any updates we do in this function, we'll still when we're in this loop, we'll see that change, and we won't visit it again. If that makes sense. Do people have questions? No? That's good. Who's going next?
I don't know. I think it's just.
Okay, so we can start looking at the next problem. The slide 25.
So for slide 25, pay attention to the constraints. Because I think that's the biggest.
Yeah. So like some of these types of problems, it's not like there's not like a n solution. This one there's probably not even an n squared solution. So you have to come up with something that may have like a long runtime, but since the constraints are low, it's still like reasonable. I think just to like solve this question in like any amount of time is like a pretty good goal, and optimizing it might be pretty hard, or like maybe impossible even.
Try this one first as the starting additional, and then yes, because I see that they're coming together. Eventually, somehow, yeah, and then you assign this. And then you for loop each zone, it's like this and everything. So here.
So what is this question? I want to know.
And then it's gonna stop. So like, this is a queue.
Okay, so given that.
So DFS is
Or given a sort.
Knowing that it's recursive, because I was thinking.
So you
it's just not real, but you have to-
not.
Yeah.
Like the
because recursion.
So how do you make?
Yeah, so BFS is the same, except it would go one level outside, like the ring would have to start. Right, so I would just like queue up, like, oh, these are the ones adjacent, yeah, and then I'll do the same kind of queue up, but only for adjacent that we have to see and are the same.
So, okay, so
I guess we can check that. Right. So we only update the visited after we clarify that it's part of the same. state.
We only find.
And then
Only-
because
only the-
part of the BFS would already see like some would eventually visit the 3x definitely like that. Well, it would visit the, well, it would see it and then mark it as not visited. Or the values would be the same.
You don't have to mark it, because you only mark it if you visit something.
Yeah, sorry, I meant to say, like, it would skip over it because the values are not the same. And it would not mark it as, right? It's not officially. It's not labeled. Okay. So you can keep those, which I think is better.
In this case, it's the same, because you're going as much as. you can.
So just preference.
Yeah, so usually BFS is.
It's the same thing you said?
Yeah.
And then you just say it, yeah, that's it.
Well, he didn't write it, but you can check the slides.
Like every that they can go to, you haven't seen. Yeah, that's literally what I said.
Yeah, you have like. Okay, so did everyone read the next problem? Okay, yeah, so I can give some hints for this problem. But I really like this problem because notice that you might be thinking, where's the graph, right? Like, does it seem like a graph problem when you read it? No, right? Okay. So the hint is you have M rules. So I just want to make sure everyone understands the problem correctly. You have M rules in the form AB, and you can swap positions A and B. So if you have a bunch of positions, 0, 1, 2, 3, 4, 5, and then you have two rules, so 1, 3, 4, 5. So that means you can swap these two numbers or characters, sorry, in the string, and you can swap these two.
Oh,
So-
is it like maybe one node can have multiple, or actually, I don't know, never mind.
So this is important because if you have A, B, C, D, E, F, then you can make the string, you can swap B and D. So you can make this, or you can also swap E and F. So A, B, C, D, F, D. But you can't swap A and B, for example. Okay, so that's the problem. And now the graph might not still be obvious, but the hint here is, what if the node is the string itself? So we have some string, let's call it S. And then it connects to some stuff. But what does that represent? So I'll leave that for you to maybe think about. What does this edge mean and what is this other thing? So we call it S prime. So we have T, and it's connected by some sequence of nodes. And you want to find the shortest sequence. Yeah, man.
So I guess each string represents a possible alteration after a single swap. So from S to S prime. That could represent a single swap as indicated by that ordered pair.
Okay, so what he's saying is if you have a string S, then S is connected to a string S prime if you can make S prime using one swap from S. Okay. So if we create a graph like that, we start from S. Then how do we get the t? Or what do we want to find from S to t? So first, if S and T are connected, then you know that there's some sequence of swaps, right? That you can get T from S. But the problem is asking what the minimum number of moves is. So first we can eliminate the -1 case because that's just a matter of checking if they're connected. And we can do this through, let's say BFS, right? We've done this before. So assuming that there is a solution, we want to find the minimum number of moves. Okay, so any thoughts on how to do that? Remember, it's a weighted graph. Each edge has 1. So that represents 1 move. And also remember that it can be many different things. Like this could be also some other S prime. This can also be some other S prime. And it can be, that's very.
I remember there being an explicit algorithm for the least sum path.
I
forgot what it's called.
Okay, well, we don't want Dijkstra's here.
Okay.
Because Dijkstra's works, that's another algorithm that works for edges greater than 1.
Oh, right.
But we only have 1 here, so we don't need that. But we only have 2 options, right? So which one do you think we should use?
Sorry, breadth.
DFS? Can you explain why? Why is
Because
it better?
at every stage, we're checking by level, or in the case of a graph, the distance. So like say we start at S, then we check, then by doing breadth, we're gonna then check everything that is at exactly 1 distance away, all the nodes that are exactly 1 distance away, and so on.
Okay, yeah.
And so by doing that, we can eventually cover a point where we, once we find that T, we know exactly how far it is from that starting point. Yes.
Yeah.
And we know, the minimum point because of the way breadth versus like a spanning kind of search.
Okay, so BFS is better than DFS here because assume we use DFS, then what DFS would do is it would go down 1 path, and let's say you found a path from S to T, right? But how do we know it's the minimum path? And the problem is you don't, because this is 1, this is 1. But let's say you travel through this path. That's 4, right? So that is a path, but that's not the minimum one, because minimum one would just be through here. So DFS is not very good for telling us the minimum number of steps. So in this case, we would use BFS because BFS first pushes through all the states that are 1 step away, so 1 move away, then pushes in all the states that are 2 steps away, then 3 steps away. So whenever we encounter T, then we know that whatever step we're on, that's the minimum. Because the property of BFS is that since it goes level by level, whenever you first encounter T, that's always the minimum number. So does that part make sense?
When you said at the beginning, like when we check if there is a T in the first place, does that require, can we use DFS there to first check if there even exists a T? Or how do we know? Like you said beginning, like with the first check.
Maybe if the breadth first fails.
I mean, you could use DFS to check whether or not they're connected, since you have to go through everything anyways.
Or is there a way to just use BFS to check if it even exists?
Yeah, you can. So let's assume that it's not connected and you run BFS from here. Then the distance here would be just infinity. So
you'll like process all the nodes, or you'll finish processing all the nodes and you'll never reach T, and at that point you can tell that there's no connection.
Maybe I should have been more specific when I said.
So imagine you have like a visited array. So this is T is never visited. So yeah. So that's just conceptually how you create the graph, because it's once you when you first read the problem, it looks nothing like a graph problem. But once you construct it like this, you see that it becomes a little easier to solve. Okay, but keep in mind that this only works because n is less than 10, so less than equal to 10. And so we have potentially the factorial states, right? Because I have to go through every single possible string, but fortunately that's not too big. So the solution would work in that case. So is everyone clear on?
Explain why 10 factorial. Like,
I did, right?
I think, no, because like, I think this is something that's like non-trivial. I think when you look for your algorithms, and they give you like a n or something. Like if, what you want to do is you want to aim for a solution that's like between 1 million and 100 million operations. And what that means is like if they give you n, which is like 1 million, you want to get an O of n solution. If they give you n, which is n squared. Oh, sorry, if they give you n, which is 1,000, then n squared algorithm is probably the best you can do. And so what Justin's saying here is that you have 10, sorry, you have 10 factorial operations. So that's like almost like 1 million. And that's why, that's how you can kind of tell like how fast my algorithm needs to be if they give you like an n.
You lost it.
Is everyone clear why it's 10 factorial? If you go through all the strings? Or if you want me to explain, you can just raise your hand. Well, but they raised their hand.
Do you know why?
Okay. Okay, sure. I'll just give a brief explanation. It's 10 factorial because let's say we have indices. So we have 10 positions, right? And the first position we can put, we have 10 different choices to put a character. But since we've already put one character here, we only have 9 different choices for the second position. And then we have 8 and so on. So the total number of combinations is 10 times 9 times 8, which is 10 factorial. Okay. Yeah, so that's how you do this. Unfortunately, we're out of time, but if you want me to briefly explain how to do the challenge problem, I could explain it right now, but that's up to you guys. Yes, you want me to explain it? Yeah. Okay, so I think the challenge problem is pretty interesting. Maybe just read over the problem briefly right now. Yeah, so does everyone understand what the problem is asking for? Might be a little confusing at first. So just to clarify, we have a graph. Let's say we have something like this, and then some of these nodes are colored red. And you can just assume if they're not colored red, they're just uncolored. Okay. And then you want to find some node X. It could be any node. If there are multiple nodes, just print out any of them, such that the minimum distance to any of these red colored nodes is maximized. So what this means is that the minimum distance of this node to any red node is 1. The minimum distance of any red node of this node to any red node is 2, right? This one is 1, this one is 1. And you want to find some node that maximizes this. So you would just output whatever index this node is. So once you boil down this problem, it becomes finding for every single node what the minimum distance to a red node is, right? Okay. But your first thought might be, why don't we just BFS from every red node? and then update every single node. Right, so we have just push this into some queue, and then we have, let's say, a distance array where every position is the minimum, and you can start every single position as n, for example, because the distance is never going to be more than n, or some arbitrarily big number. And then for every time you BFS, you update. So this would be, you can say 111. So this is actually not the greatest example, but let's say we have another node here. So this node would be 2. So let's just say it's this position. If we push this node, this red node in first as our starting position. So it'd be 2, right? But then we push this one in, and then we get to this node again. And we find that the minimum distance is 1. So 1 is smaller than 2, so we just update that. So this solution works, but the problem is that the time complexity is very slow. So it's for every single node, you go through every single node, so it's n squared, right? But according to the bounds, n is 100,000. So you would have a lot of numbers. Yeah, like 10 to the 10. So that is way too big. So you're going to need a faster solution. And I guess since we're running out of time, I'll just go over what that is. What we can do here is what we call a multi-source BFS. So here you can see that the sources are the red nodes, and we want to BFS from every single one of them. But we're wasting a lot of operations since we're going through every single node over and over again. So if we have a queue, why don't we just push in the indices of all of these red nodes first? So let's assume it's R1, R2, R3 for the indices of the red nodes. So first push all of them in, because every one of them is a starting state. Okay, and then you run your BFS. But how is this different than a regular BFS? And if you think about it a little bit, it's because first you take the first position, so the first red node, and then you visit all of the nodes that are one distance away. And then you visit all the nodes that are one distance away from the second red node, and then the third red node. So think about them as like a ring around the node that expand. But when these rings collide, you know that if you've visited a node already, because we pushed all of these sources in first, then it must be closer to some other red node. So that's the crucial part, if that makes sense. So we have, like, think about a bunch of dots on a plane. Like, so you have small circles that grow bigger, like this. And so when two of them collide or intersect, that's when you visit a node that's already been visited. And you know that at this point, if it's visited already, then it must have been at a closer distance or equal distance to some other red node. And that's just the property of a BFS. So if it's visited already, you just return. Otherwise, you update your distance array. Okay, and then the time complexity for this becomes O of n because you visit every node once. So does that make sense?
I think you can also think of it as like creating a new node and connecting it to all the red nodes. Is that right? Have you seen that? And you start your BFS with that new node.
Yeah, I guess you could
artificially generate it.
Yeah, you could do that.
I think it's just easier to understand.
Okay, sure. Yeah, so what he's saying is create a new node. So this is just a temporary node that connects to these. And it's the same thing if you just start from here, except make sure you don't include this edge as a distance.
And now you just calculate a distance to that temporary node, but that's the same as a distance to any red node plus 1. Right? And now you just hit the same BFS algorithm, but with this new node added.
Okay, yeah, so that's just one of the tricks you can do with BFS. I don't think it pops up. I don't think I've ever seen this pop up in an interview, but it's just a nice trick to know that you can push multiple of these starting nodes in a BFS. Or you can also use this trick of just rearranging the graph and then running the BFS on it. Is there any questions?
Oh. Are you given the location of the red?
You are.
Oh, okay. I didn't read the problem.
Okay, does that answer your question?
Yeah.
Okay, yeah, so that's it for today.
And for all